So now we can draw the general profile. Let's draw a non-dimensional profile. On the x-axis, we have u1 over u, and here we have x2 over h. So when k is equal to 0, we know the profile will be a linear one because the pressure doesn't take a part in the flow, right? But when k is bigger than 0, then the pressure is a proportion. So the profile will look like this, right? This is when k is bigger than 0. Contrary to this, if k is smaller than 0, then the flow is hindered. The last thing, we can calculate the flow rate or the discharge. This thing we should, to get this, we need to integrate the velocity on the area, right? The area here is just the x2 direction. We wrote the lowercase u here means we are considering unit depth. Well, I should say unit width in the x3 direction, right? So we can only consider the x2 direction in the integral. So it will be something like this. If you do the integral, you will get this result. Well, this result is very simple. First, we know that the flow can be divided into a couette part and the Bossuet part, right? The couette part is just this. So in order to get the flow rate resulting from the couette part, it's just half the velocity because that's the average velocity, right? Times the area. For the Bossuet flow, we know that the pure Bossuet flow itself is a parabola. And what's the average velocity of a parabola? I can tell you. The mathematical result is 2/3. It's 2/3 of the max velocity. So you can pull in half h in the equation, in the solution we got to get the max velocity of the pure Bossuet flow, and you time it by 2/3, and you will get the average velocity resulting from the Bossuet part. Okay? So if we write out the average velocity, it will be q over h, right? And it will be half u plus kh squared over 12 mil.